You know, the last time, well, I ended with a different theorem, which I'll repeat after this, but we were talking about this here. And so, this part we did last time. Do it for this one. So let's do this one. Starting with the assumption that I had G idea. Look over my notes. I think I must have had some kind of out of body experience. I don't, because it's actually much easier than I made it out to be. So on the other hand, if I is G ideal, then of course this means that I is prime and R mod I is a G domain. This will be both plus to the next statement. And so there exists, well, we need to set up here. There exists a maximum ideal and must be a form M mod IX, where M in Rx is maximal. Such that when you intersect this maximal ideal M mod IX with R mod I, you get the zero element R mod I. So let me pull a translation on this. So note that I is contained in IX, right, as a set of elements, which is contained in M, because by necessity, by the correspondence theorem, that M is an ideal, maximal ideal already contains IX. Therefore, I is of course contained in M, so I is contained in M intersect R. Okay with it? And the other containment actually follows from this, right? Also, since M mod IX intersect R mod I is 0, then M intersect R must be contained in I. Right? Because let's suppose that you have something in M that's also in R, right? Well, so the coset that corresponds to M here intersect, because of this right here, this means that whatever this M is has to be the 0 element here, and therefore in I. Right? So anything that is in M and here, it corresponds to coset here must be in I. So M intersect R is equal to I, and there's your maximal ideal that contracts to I. Okay. Any questions on that? So let me give you actually technically the last thing that I wrote down last time. Theorem 4.3.12. Let M be a maximal ideal of Rx. And suppose that its intersection down with R is maximal. So you get the maximal ideal of a polynomial ring, and you're still lucky that it intersects actually to a maximal ideal downstairs. This is a fairly common occurrence, actually. It doesn't always have to happen, but it happens quite frequently. Then M as an ideal, as a maximal ideal in Rx is generated by these elements of N, right? So basically it's generated by the constants and toss in one more polynomial, right? And what's more, so remember so basically what this says is this maximal ideal that intersects down to a maximal ideal here can be generated by that maximal ideal, these constants here, and one more polynomial, which is kind of cool. And I can select this polynomial special. Additionally, F can be selected via monic polynomial. And such that its corresponding polynomial mod N that so in other words, when you take its so let me write this down more explicitly here. Right. So its reduction. So for example, if you look at N CX, this is such a maximal ideal, as a matter of fact, right? But your maximal ideal could be disguised in a certain sense. This is equal to 5 7x plus right. This ideal is actually the same thing, right? Because if you look at this ideal generated by 2 in this polynomial, well, the 2 allows you to actually squeeze these out, right? Because they're already in the ideal generated by 2. And you can actually use the 2 and use the Euclidean algorithm to actually sort of pare this down to this more streamlined polynomial. And that's essentially what's meant here, right? Or whatever. There can be many other polynomials generated. For example, this maximal ideal is generated by the ideal generated by 2 streamlined, or this other one, but you can select this, you can revamp it so that it's irreducible, in this case, modulo 2, right? And monic, if you like. And then let me point out reduce the problem of this theorem So I want you to think about this. This isn't too hard. This is actually an important technique. Reduce this mod n the case where n equals 0. So start off your theorem here. You've got this maximal ideal. N is the intersection here. When I say reduce mod n, what I mean is I pass to and the role of my maximal ideal m right. Right, m reduced there. So basically just quotient out by n. So this problem now becomes m mod nx in r mod x, and the n becomes 0, right? And notice that this is now a much easier theorem, because now in this situation, what you have is R mod n is a field. Right. Because remember, n was maximal ideal of R, so R mod n is a field. And now, basically, what you have to do is now show that a maximal ideal n comma f, but here n is 0. Because remember, now field over x is the principal ideal domain, n is 0, and the rest really follows, because what happens here is this thing is a prime ideal, non-zero prime ideal to PID, so it's automatically maximal. And since you're over a field, you can always assume that the polynomial is irreducible and monic. Okay. Any questions? You look extremely disturbed.
I'm not extremely disturbed. I do have one question. So
Yeah.
when you say that n is the intersection of m and r and it's a maximal ideal, are we assuming that, or is that always the case when you have a maximal ideal?
No, it's not always the case.
Okay.
We're making that assumption.
Okay.
Right, exactly. So as a quick sort of
Example.
example, if you look at because if you look at this crazy range, so coefficients are power series over Q, which actually is the G domain, which is why I do this, and polynomials over that. Then if you look at the ideal curve by xt minus 1 is maximal in R. This is actually a maximal ideal. We talked about this example before, right? But if we call this M, generate, if you look at, in this case, M intersect R is the 0 actually, right, which is not maximal. So in many cases, so for example, if you look at polynomials of the integers, that always happens, right? But sometimes it doesn't. Okay. So now we're going to up the voltage here, this theorem here. We can say a bit more. if R mod N. Well, what do I know about R mod N? I know it's a field, but there's something. What does every algebraic geometry like to say about their field? Well, this obviously is universal, but a lot of times they like to work over algebraic closure, right? So let's kind of revamp this. Algebra. Oh, by the way, does it appeal to you what you can say? Look at the content of the theorem here. You can generate this maximal ideal by N and F, where F can be monic and and its reduction mod N can be irreducible. So I can just take F to be that reduction mod N. What can you say R mod N is algebraically closed? Yeah, in fact, if it's algebraically closed, not just anything now can be irreducible, right? The only irreducibles are linear polynomials. And so let's up this a little bit. 4.3.13, suppose well, let me put it this way. In 4.3.12, if we also assume R mod N is algebraic closed, then M then we can actually do it this way for some A. Right, because the only irreducibles over an algebraically closed field are the linears. Anything of higher degree can be broken down. So that's kind of cool. And if any of you have ever seen the Stone sites before, this might be kind of coming a little bit into focus. And if you haven't, don't worry about it. So let me point out that this will be useful for us. If you have a domain, then a maximal ideal is a G ideal. In fact, you don't even need a domain there really. So if you have a maximal ideal of a ring, then it has to be a G ideal. And the reason is R mod M is a field, which is trivially a G domain, right? So maximal G ideal. What if all G ideals are maximal? If that is the case, which it isn't always, but if it is the case, we can say a bit more. And we will define, this is a useful class of ring. We're going to prove, so get another step up, some stuff about to kind of finish off the building to the Stone stats. We say that R is a Hilbert ring. Yeah. Every G ideal is maximal. So maximal ideals, always G ideals, but if the converse is true, if every G ideal has to be maximal, then we call this animal a Hilbert ring. Sometimes it's called a Jacobson ring, sometimes it's called sling blade, but we're going to prove some nice properties about this and use this to finish off the Millstone size. First, we need something that's going to help us in our pursuit of this. This is a famous little lemma. This comes up in a lot of, this is a very useful thing. If you, by the way, if you took my advice and tried to figure out, you remember how we said that, I gave you a theorem that said, that if you have a semi-local, well, actually semi-quasi-local domain, then any invertible ideal is principal, right? We only proved that for the local case. Doing something like this will help you because I gave you a little challenge. I said, how do you do it with more than one? But finally, many maximal ideals. Let P1, P2, Pn be prime ideals. I guess we can similar distinct if you like. And suppose that I is an ideal that's contained in the union. Then I is contained in one of them. And this is often called prime avoidance. This is kind of a nifty little theorem because it says that if you, and actually, let me give you an example before I prove this to show you. So what it says is if you have an ideal, I guess I need something more colorful here. Basically, what prime avoidance says is whoops. What prime avoidance says essentially is that can't happen with prime ideals. Because if you have an ideal that's contained in a union, so if the yellow one's a prime, the ideal is contained in the union, it has to be contained in one of them. So if I drew you a picture, this little kind of diagram and said that I is an ideal, what can you tell me about these other ideals here? You can tell me, well, they can't possibly all be prime, right? Because prime avoidance guarantees that. So this basically the content, right? And this isn't obvious just from my picture, right? But if you have an ideal that's contained in the union of a finite number of primes, it has to actually be contained in one of the primes. Right? Let me illustrate something to show that the hypothesis about the primes being well, I guess that there's a number of ways that you can do this. Can anybody tell me why you're going to need finiteness? Right, that is why you need only finite times.
If you just took all of the prime ideals and took the union over all of the prime ideals, well, pretty much any ideas. Yeah, any ideal is going to be contained in one of those since it's going to be contained.
Well, that's right. I mean, so for example, yeah. So for example, you know, you take all the max values. I can give you something concrete. So you guys remember this sequence domain we did, where we took P1 and we took a prime P and we built this domain and we split this into say P11, P 2. Let's see, I can tell you what level 7. And then I can split this into P 2, yeah, mine is P21, Yeah, my index is really horrible here. Let's do it this way. Let's go Q1. Yeah, I'm running the same problem here. Q1, Q2. Let's say Q1. Yeah, it's. Et cetera, et cetera. So you start with this prime, right? In fact, you start with like a local PID, and then you jump to a quadratic extension where this splits into these two primes. So in this second tier ring, then P is Q1 times P1. Now, in the next step, you leave Q1 alone and you take P1 and you split this. So in this third tier ring right here, Q1 remains prime and P1 is the product of these two. Now you jump again, and at this stage, P3 is the product of these two, Q2 remains prime, and Q1 remains prime, and so forth. There is, of course, the zero ideal, which is prime here. And the prime ideals are this one, this one, this one, and the stalk all the way up. Notice that the stalk is not contained in any finite collection of these. However, the stalk is actually contained in the infinite union of these primes, right? Because, for example, Q1, that ideal contains this because it divides it. Q2 contains this, Q3 contains this. So if you look at the infinite number or the infinite union of Qs, they will contain this big prime ideal here. However, obviously this big prime ideal here isn't contained in any one of these Qs, right? So you definitely need, the theorem itself is not obvious, I don't know, even for a finite many primes, but this little picture shows that it works. Well, I'll give you one more example. Right, so it's gonna be UFD and all right. So actually, let's look at this right here. Here's another example. This ring is a UFD. And actually, I know Grant knows that because you were in the right room in the conference at the right time. But a power series ring over a field of any finite number of variables is UFD. Power series are tricky with that, but if you don't like that, you could change that to power series in two polynomial two variables and localize the maximal ideal. This is UFD. Now look at the maximal ideal M. It's the ideal determined by x1 and x2, right? Now, list the prime elements. Not zero, but it doesn't matter. You can list zero too. So, list all the prime elements and consider the union notice maximal ideal has to be contained in there, right? Because this ring is a local ring, which means that everything that's not unit is contained in that maximal ideal, right? So take your favorite element of that maximal ideal, whichever element of that maximal ideal you want. This is UFD factored into primes, right? And it is contained in every one of these prime ideals that's a factor of it, right? So the union of all these prime ideals contains the maximal ideal. Agreed? However, it's pretty clear, isn't it, that the maximal ideal is not contained in any single prime element, because the prime element would have to divide both x1 and x2, right, which is impossible. So, yes, indeed, we do need only finitely many prime ideals, but again, I don't find this super obvious. So let's see why prime avoidance is true. We proceed. Let me write down the case n equals 1 since I erased the theorem. If I is contained in P, then I is contained in P1. Okay, so 1 wasn't so bad, was it? Right? Now, I'm going to make an observation for the higher case. So we're going to go beyond 1 here. Now, for all k between 1 and n, note that pk remove pi is not empty. And this is kind of an important piece of the puzzle here. So if you take any one of these primes, any one of my n primes, and remove the union of the rest of them, there has to be something left over. If not, then some k, we have that and so that would mean that pk is contained and we will be done by induction. Right, because now we're unioning one less prime. And so if pk is contained in that, it would have to be contained in one of them, right? So let me also point out that a similar argument shows that, in fact, for all k, we can select for all k, xk and pk minus the union of the primes that aren't k, and also an I. The argument here is very similar to the one that we just did, showing that that pk minus the intersection of the union of the other ones is empty. Because if this set is empty, then I is contained in the union. And again, we go back to our inductive hypothesis, because we've reduced the number of primes that we're unioning by 1. So let's make this selection. So recall we picked XK in PK, but not the union of the other. Now I'm gonna take this apart, and I'm gonna do this for n equals 2 and then bigger. N equals 2 is a warm up, and n equals bigger is basically the same thing. So if let's take now let y be x1 Now, what do I know about x1 plus x2? Well, they're both in I. All right, so the sum of x1 and x2 has to be in I. And of course, we're assuming that this is in P1 intercept P2. Now, here's what the problem is. If y is in I, then y is in P1 or y is in P2. Correct? Because I is assumed to be contained. Well, if oh, I'm sorry. And I did get that right. Yeah, I just did my symbol right. If y is in I, then y is in P1 or y is in P2. So if y is in P1, anybody see what the problem is? If y is in P1, then x2, which is y minus x1, is in P1. And this is a contradiction, because x2 is in P2 exclusively, not in P1, right? And there's the same problem if you assume that y is in P2, because then you would get that x1 is in P2, right? So this is a contradiction, and the case n equals 2 is established. For the larger case, for the more general case, suppose n is bigger than 2. Well, what I do is I just make a slight little change here. Let z equal oh, wait a minute. That's not I want more. So here, what I'm going to do is I'm going to do something slightly different. Remember, these x1 is in P1, but not the rest of them, and so forth, so on. So this thing is in I, because notice that each of those x sub i's are in I. So this is just like before, it's in I. Note that z is not in P1. Because if this is in P1, the fact that this is in P1 gives you that this product is in P1. And now you have problems. So xi is in P1 for some 2 when I n gives you the right? So there, actually, that's a key place where we use the fact that P is prime ideal, right? Notice that z minus x1 is in Pj. Well, so z is not in one, so you can look at that. Notice that x, z minus x, one. Okay, for all to the bigger than one. Because it's the product of those other ones. But since x1 since x1 is not in PJ for any of these j's, then the z cannot be either. Therefore, right, because we've already established that z is not in P1, and it can't be in any of the ones bigger than one, so z can't be in any of them. So z is not in I. And then, so we've got the prime avoidance. Okay, any questions? Okay, so back to this business with the Hilbert rings. Theorem.
If there's a longer proof of this that doesn't use induction, if there's any direct proof of this that doesn't use induction.
Let me say yes. Well, let me say I can't repeat it. It's just, I'm a big believer that there's always another way, right? And I'm sure there must be. Induction is very natural though, right? But I would feel sure that there's some, something using complex analysis. Who knows? There's all kinds of wacky things out there. So I would never say never, right? So. Okay, there are 4, 3, 6. Let R be a Hilbert ring. And remember what that means is all the G ideals happen to be maximal ideals. Then the radical of I is the intersection. Okay. This was just a quick observation. So what this says is in the Hilbert in a Hilbert ring, if you want the radical of an ideal, all you got to do is figure out the intersection of all the maximal ideals. So you don't need those intermediate primes intersecting. So intersecting the smaller primes that contain I sort of cut you down quickly and more efficiently. This says really intersecting the maximal ideals is enough. You don't have to worry about intersecting the extra ones because the maximal ideals will do the job. Notice that in general, this is the intersection of the prime ideals containing I. You can shortcut this down here. So recall the radical I equals the intersection of this is a result that we proved a couple of lectures ago. That the radical ideal, we refined it from all the primes containing I to all the G ideals. That is, from the primes that contain I that are the G ideals. But guess what? In a Hilbert ring, the G ideals are the maximal ideals, and so there you go, right? So it's just it's pretty much a matter of definition. Okay, proposition. 4.3.17, let R be a Hilbert ring. So here's a couple of pretty properties about this, shows some niceness of the Hilbert rings. Number one, every homomorphic image of the Hilbert ring is still a Hilbert ring. So in other words, if you take any ring R, it's a Hilbert ring, R mod I is still a Hilbert ring. That's cool. And number two, either R is zero dimensional or it has infinitely many maximal ideals. Either R is zero dimensional, which means, remember what that means? That means that all prime ideals are maximal. So it's stubby, right? Your primes are exactly the maximals. Or R has infinitely many maximal ideals. By the way, after I've done all this, can anybody give me an example of a Hilbert ring?
Z,
What's that?
Z.
See, that's exactly what I was thinking, right? Because, think of your only choice in Z are, for the G ideals are zero in the maximal primes. Well, zero is not a G ideal in Z because Z is not a G domain, right? But all the maximal ideals or all the other prime ideals are maximal, and so that's a good example of Hilbert ring. Notice that Z falls under the second condition of condition two and not the first. Okay, so let me see here. I think I can get through one, and that'll probably be appropriate here. So it is interesting that every homomorphic image is a Hilbert, right? So let's see this. So let's suppose R is a Hilbert ring. And I and R are not real. It should be kind of a correspondence theorem thing. Let P mod I be a G ideal. Right? So what we have to do is show in R mod I that every G ideal is in fact maximal. So look at P mod I, and suppose it's a G ideal of R mod I, then P is a G ideal of R, and hence maximal. Therefore, P mod I and R mod I maximal. And that's all you need to know, right? What we'll get to next time, but I think this is probably a good place to stop for the day. Any questions out there? Any questions? All right. Well, y'all have a good one, and we will see you on Wednesday.